Okay, so in this recording, what I'm going to do is finish chapter 17. So we've already covered section 17.7, but I just want to mention this. We said that when delta G is negative, that means that a reaction is spontaneous. So the free energy goes down and the reaction is spontaneous. Just because a reaction is not spontaneous doesn't mean that it won't happen. It just means that it won't happen without outside help. So if delta G is positive, you can still make that reaction happen by doing something to help it. So you could potentially add energy by maybe increasing the temperature or even decreasing the temperature, or you could couple it to a reaction that has a negative delta G. So I just wanted to finish up that section, even though we've essentially covered it. All right, now in section 17.8, we're going to look at how free energy depends on pressure. So because we're looking at pressure, we're going to be looking at gaseous systems, systems that are comprised of gases. So we know that a system will proceed in the direction that lowers its free energy because delta G is negative. But the free energy of the reaction also changes as the reaction proceeds. And it actually depends on the pressures of the gases. So the equilibrium the equilibrium point of a reaction is defined as the point where the free energy value is at the lowest. Okay, so equilibrium means free energy is at its lowest. All right, so we're going to look at how that applies to pressure. So remember the formula for delta G, because in order to understand this slide, you have to remember the formula for delta G. So we need to remember that delta G is equal to delta H. Ooh, I'm not drawing this very well. It's hard because, again, I have to use my cursor to draw. Minus T delta S. So if you want to know how pressure affects delta G, you need to look at how it affects delta H and how it affects delta S. So enthalpy or heat is not dependent upon pressure. But entropy does depend on pressure because the entropy will change with a change in volume. Okay, so again, if there's a large volume, the entropy is greater because there's more disorder than if there's a small volume. So a large volume corresponds to low pressure. A small volume generally corresponds to high pressure because pressure and volume are inversely proportional to one another. All right, so this is an equation, and we're not going to use it in this form a lot because this would be the equation for a single gas. So the free energy of a gas at a certain temperature and pressure is equal to the standard free energy plus R, which is the universal gas law constant, times temperature, times the natural log of the pressure. And pressure has to be in atmospheres. Okay, so pressure should be in atmospheres. Now, how does this apply to a reaction? Well, we want to look at all of the gases in the reaction, and you don't necessarily need to know how I get from this equation to this equation, because this is the one that we're primarily going to be using. Okay. So delta G is equal to delta G standard. We talked about how to calculate delta G standard. You can use that summation if you know T or if you know delta S and delta H. So there's a number of different ways, but we did several problems calculating delta G standard. Plus RT times the natural log of Q. Now Q is the reaction quotient. It's the same thing as an equilibrium constant, except you're using, it doesn't apply to, well, if Q is equal to K, then it's at equilibrium. But Q is just using whatever pressures you're given, whether they're at equilibrium or not, okay? So we're going to use that equation to get the delta G of a reaction and see how it depends on pressure. And the next problem is problem number 14. And again, I'm not going to be able to do that right now because I can't write it all out in this program. So I will provide you with another video that shows how to do exercises 14 and then exercise 15, which is the last in-class exercise. All right. So what does delta G mean? Well, again, if delta G is negative, we said that the reaction is spontaneous. But even if delta G is negative, the system may not go to completion. Even if delta G is positive, the system may still move toward the products. So just because delta G is positive doesn't mean the reaction doesn't take place at all. And just because delta G is negative doesn't mean that the reaction goes all the way from reactants to products, because the reaction spontaneously seeks equilibrium. Okay, so this would be a case where, using this analogy of the ball rolling down the hill, the ball is going to roll down and land at point B in this reaction, because point B is the only place it can go to. So this would be something like a phase change, where A is water, or is ice, and B is water. When the ice melts, it can only go to water, only has one choice. Okay, there's no intermediate, and we know that the water has lower free energy because it has more disorder than the ice. Now, case number 2 would be a chemical reaction where B may have a lower free energy than A, but there may be a point that we call point C that's still even lower in free energy. So the ball may start at A, go to C, go to B, but eventually it's going to go back to C. So this would be like equilibrium. C would be equilibrium. So when you think about equilibrium, it's the condition where the rate of the forward reaction is equal to the rate of the reverse reaction. So this is the forward reaction, the ball's going down to B, and this is the reverse reaction. So if you would roll a real ball, it's going to roll back and forth until finally it's going to come to rest at C. All right, so C would be considered the equilibrium point. All right, so the equilibrium point is the point in a reaction or in a system where free energy is the lowest. Okay, so it's the point in a system where free energy is the lowest. And in this case, they're just having you look at gas A turning into gas B. All right, so we're not going to spend a lot of time on this, but what you need to know is that if this is a spontaneous reaction, the free energy of gas A is going to go down, the free energy of gas B is going to go up. Why is that? Because the pressure of gas A is going to decrease as it decomposes. The pressure of gas B is going to increase as it's formed. Eventually, you'll get to a point where the free energies are the same, and that point is equilibrium. And at that point, the pressures are also going to be the same. Okay, so the equilibrium point is the point where the free energy of the products minus the free energy of the reactants is 0. So the change in free energy is 0. So when delta G is equal to 0, we know the reaction is at equilibrium. And we kind of did this with phase changes. We said that during a phase change, delta G is equal to 0. All right, so I'm just going to go to this slide. We're going to go over this one kind of quickly. Don't pay too close of attention to the diagrams, but this equation right here, all right, gives us the relationship between delta G and equilibrium. So remember, the original equation was delta G is equal to delta G standard plus RT ln K. We said at equilibrium, delta G is equal to 0. Equilibrium is when Q and K are the same. So at equilibrium, delta G is equal to 0. So you would get 0 equals delta G standard plus RT ln K. And then if you subtract delta G standard from both sides, you'll get negative delta G standard equals RT ln K. Multiply both sides by -1, and this is the equation that you get. So really, all you need to worry about is this equation, because we will use that. It can be used when you know the delta G standard, or the delta G of formation, to calculate the equilibrium constant. Or if you know the equilibrium constant at a certain temperature, you can calculate delta G standard for a reaction. Okay, so let's see what is going on here. If delta G standard is equal to 0, so looking at this, 0, we would get 0 is equal to negative RT ln K. Well, the natural log of 1 is 0, so we know that then equilibrium constant must be 1. And so K is equal to 1. When delta G is less than 0, it's negative. K is greater than 1. That means the equilibrium favors the products. In this case, equilibrium favors neither reactants nor products. When delta G is, I'm sorry, I might have said, when delta G is less than 0, delta G is negative, the products are favored. When delta G is positive, the reactants are favored. K is less than 1. Okay, so again, I can't do in class exercise 15 right now. I will do that. This is the last in class exercise, and I'll do it on the next Show Me. We're almost done with this PowerPoint. All right, we're not really going to spend a lot of time on this slide at all. Don't really worry about it. The thing I want you to know is that if you plot a plot of the natural log of the equilibrium constant versus 1 over temperature, it will be linear, and you can use that to get delta H, and then to also get delta S if you know one or the other of those. All right, so really you don't need to worry about this equation at all. In some years, I even skip this slide. Don't worry about it at all. You won't be tested on this at all. Okay, the last section goes over the relationship between free energy and work. Now, and it gives us what really the definition, what free energy means, okay? So, free energy is equal to the maximum amount of work that a system can do. So in a spontaneous reaction where you have a negative delta G, we say that the amount of energy, the amount of delta G, is the energy that is able to do work. In a non-spontaneous reaction, delta G equals the amount of energy that's needed to make that process occur. Okay? Now, we can tell whether a reaction is spontaneous. Any pathway that a reaction takes always wastes some energy as heat. We're looking at things that are perfect, but in real life, things are not perfect. Any real pathway wastes energy as heat. All right, so we can talk about a process being truly reversible, where the universe is exactly the same after the process as it was before the process. If you have a process that cycles, so it goes back and then it goes forward and then it goes back. Kind of think about recharging a battery. In a truly reversible process, we say the universe is exactly the same as it was before a cyclic process occurred. In an irreversible process, the universe is a little bit different. Now, all real processes are irreversible. So again, think about charging a battery. You plug your phone in and it charges the battery. Eventually, your battery is not going to hold a charge as well as it did. It has a limited number of charges available to it, because every time you charge that battery, some of the energy is wasted. It just is. Some energy is always wasted as heat, and it's used to increase the entropy of the universe. So, a funny way of looking at the first law of thermodynamics, or of the laws of thermodynamics, the first law is the law of conservation of energy. So another way of stating that is you can't win, you can only break even. So you can't get more energy out of a process, you can get as much out as you put in. The second law says you can't even break even, because as we use energy, we degrade its usefulness. The entropy of the universe increases, and the energy that we have used we can't get all of it back. All right, so this is the end of the chapter 17, and you should then watch the Show Me video demonstrating problems 14 and 15.